Okay, hello everyone. Welcome to a physics project working session. And Jonathan and I are intending to talk about quantum computing and some of the things that Jonathan has been finishing off with our quantum computing framework and its compilation to our physics project models. And Jonathan, I think we were talking a little bit about kind of doing NKS-like things with quantum gates and asking what do the simplest quantum circuits actually do? And then maybe we can focus on that as a way of thinking about how our quantum computing framework works. But maybe you want to start off by showing, I mean, construct a simple quantum circuit and show us how to figure out what it does.
Sure. Yeah. Okay. So, right. Yeah. So this is the circuit functionality. I was just mentioning, I was working on this today, trying to get better rendering for our circuit diagram, so that we should now have much better gate icons and rendering and things than we did in the previous version of the framework. So we can test that out now.
Okay.
But okay, let me show you the kind of the basic pipeline for this. So, Stephen, do you have a favorite quantum gate?
I don't know. Let me see the inventory of all of them.
Oh, okay. So if you go to, this is the downside with only sharing one window, but if you go to quantum discrete operator,
why don't you share multiple windows that way? Is there a reason not to?
Okay, I guess there isn't a reason not to. Hang on, let me do that. 1 second. Sorry, I have to unshare and then reshare desktop 2. Okay, right. So can you now see a
Yes, you can. But why don't you can just maximize your, I don't know, just make your window bigger. That way nobody has to be exposed to the beauty of your desktop. Just make your Untitled 6 bigger.
Okay, sure. No, it's a slightly embarrassing collection of screenshots on my desktop. But anyway,
well, fine.
Sorry.
That's why I'm suggesting you make the window bigger.
Right. Anyway, so yes, on the documentation for quantum discrete operator, here's the inventory of named gates that we've got.
Okay. All right. So okay. So C naught and one other are universal. Is that right? There's a combination of C naught and something else. What is the minimal kind of universal set?
Yeah. So well, okay, there are some which are universal just with a single gate, right? So like the Deutsch gate is universal in itself, but that's a 3-qubit gate and it's quite complicated. I think you're right. So I don't remember offhand. We'd have to look it up in a moment. But yes, you're right. I think C naught and I think it's a single qubit gate. It might be something like Hadamard are universal. Yeah.
Okay. Well, but maybe we should try to look at, for example, for the C naught gate. Let's just try and see what we can build out of C naught. Well, let's just try taking those, C naught and Hadamard. Let's see what we can do with those two.
Right.
So we would generate all possible circuits with of that form.
So Clifford plus T, which is C naught Hadamard, and the S and T phase changes is universal. So that's notable because they are, with the exception of C naught, those are all single qubit gates.
Right. Right. As I recall from thinking about this like millions of years ago, you're basically trying to build up arbitrary phase. You're trying to synthesize arbitrary complex number phases, and you can do it with non-commensurate rotations. Is that right?
Right. Yeah, that's the idea.
Okay. Well, so let's take a look at the ones that you just mentioned, and let's just see how a C naught works to begin with.
Right. So C naught obviously has 2 inputs, right? So we're going to declare a quantum discrete operator C naught with order 1, 2. Sorry, it's going to have to pull in the resource function because I just restarted my kernel. Okay, so there we go. That's that. That's the operator. Its matrix representation. If we wanted to, we could say, let's create a state. Random pure state with 2 qubits. We can just say O1 applied to S, and we get the output of that.
Okay. Now, if I want to see that in the computational basis, how do I do that?
Okay. So by default, all of these things will be in the computational basis, right? So if we request out the basis of like this state, it's and we get its basis element association. you'll see that it is in the
No,
computation.
poor Irwin should get his umlaut.
Oh yeah, so this he did in the original version of this. The function repository team came back and said we don't normally accent things. So the way the thing's set up is Schrodinger with an accent and Schrodinger with an OE are all supported. They're all treated as
Okay,
equivalent.
all right, whatever.
The
Fine.
default
The function name probably shouldn't be accented. Yes.
But if you change the picture to that with an umlaut, it's everything still works.
Okay, all right. Anyway, so this is now.
So this is in the computation. So actually, you could see. Okay, if we get S, we can say amplitudes. You can see this explicitly written out as an association of here's a tensor product of two computational basis states, and here's the associated matrix element.
Why isn't that an exact number, by the way?
Because this is a random pure.
Oh, okay.
So I mean, if we used an actual state, so like if we did, I don't know, GHZ or something, then yeah, they'd be proper numbers.
Okay, let me understand what this did. Okay, so this is quantum discrete state with 3 qubits. Okay, and those are the amplitudes for those in that basis. Those are the amplitudes for that state. Those states.
Right. So the idea, the design idea was actually this was originally your design suggestion, which turned out to be a very good one, was that the minimal representation of a state or an operator is just an association, where the keys of the association are the basis states, the basis elements, and the values give you the vector, the state vector, or the matrix, or whatever.
Okay.
So if we say S state vector, it will literally just return the values of the association.
Okay, that makes sense. All right, fine. So we're using, I mean, normally you go to all kinds of gymnastics in quantum mechanics to deal with the fact that you don't have an association. You just have essentially positional information in a matrix to define what basis element a particular matrix element is associated with. But since we have associations, we don't have to worry about that.
Precisely, and so everything. Okay, the open secret about the QC framework is that literally everything is an association. So like an operator is really just an association. If we say the discrete operator, we can get its operator form, and here you can see. Okay, it's a bit more complicated, right? Because we've got now this is a two-dimensional matrix. So we've got a ket tensor product with a bra.
Very nice, yeah.
And that gives us the matrix elements. So again, if we when we request out matrix, oh sorry, I already did it below. All that's doing is it's just taking values and then reshaping.
See, what's interesting about this suggests an idea of two-dimensional associations, which is not a concept that we've really, I mean, this is, in a sense, lots of relational algebra in databases is sort of related to things like this. But what you've got here with the fact that you've got that, that outer product thing, yeah, that's interesting. Okay, I mean, I'm just thinking about what that means because we could imagine an operator right now. The combining keys in an association. Normally you'd have an association of associations. What you've done here is to flatten that into a single association with composite keys.
Right. Exactly. Yeah.
And we do have operations that do that, but I don't think that we have really developed the calculus of, I mean, that would be an interesting thing for something like dataset, to be able to turn, if you say, rather than saying, I want element blah, element such and such of element such and such, to be able to do this thing. Okay, that's an interesting idea. All right.
Right. So your set of keys is somehow some kind of Cartesian product.
Exactly.
Yeah. Yeah. Okay. I agree. That's an interesting data structure.
Okay, but that's it. Somebody should make a note of that, and we'll come back to that in a different discussion about data structures. Okay, so now let's see this gate dance. What can
right? Okay, so what I wanted to show is just. So I mean, in a sense, we've seen the gate dance by just applying it to a state, but that's not very interesting. So what I want to show is if we take quantum circuit operator and we put O1, the C0 gate, into that, so we get out a quantum circuit operator. So then we can ask for its diagram, and we get a nicely typeset C0 gate. And if we swap the wire positions around, it will swap the wire positions around on the diagram. Or if we change this to 1, 3, we'll get we'll now get a three wire circuit diagram.
Nice.
So okay, we were going to do the Clifford plus T example, right? So we should probably have a couple of other gates. So we've got a C0 gate. Let's have a Hadamard gate somewhere. So like Hadamard, I don't know, on qubit 2 maybe. And then let's have an S phase change gate on qubit 1.
Oh, you just said O2 there. You just said O2.
Sorry, yep. There. And let's do a, I don't know, this is going to be a fairly boring circuit because it's all just going to be linear. But let's do, I don't know, a E phase change on qubit 2 again or something.
Mm-hmm.
Okay, so that's our circuit. And internally, this circuit representation is just, like any of these operators, is just, well, we could get its matrix representation. So this is now just going to be,
Right, but that's a horrible mess. But now let's see it with its actual keys in it.
Right. Okay. So if we say, wait, let me get this right. So it would be operator. Yeah, there we go.
Yeah, well, that's nice. That's very nice and explicit.
Right. And so each of these quantum circuits is internally, it's given by an association where that association is derived by a combination of compositions and tensor products of the individual constituent operators.
So just so I understand, I mean, I've never seen an S matrix as explicit as this in some sense, or an evolution matrix. This is basically saying those are the initial and final states that are in the key specification.
Yeah.
And which I'm not quite sure why we're doing them with the ket first and the bra second. Is there a good reason for that?
No, I mean that's.
It would seem more natural to have the bra first, wouldn't it?
Yeah. That could make sense. Yeah.
Okay, so wow, I've it really is like an S matrix. I mean, it's just like initial to final state transformation explicitly given. Exactly. Okay, so now how do we make these things? I mean, like, let's say we're going to do some non-trivial quantum algorithm. Again, you've got 5 minutes with a quantum computer. What are you going to do with it? Well, actually, for this particular thing, maybe we can just see it. Can we see it actually, quotes, run? What would it look like if we fed this to a quantum computer? What kind of thing will we see?
So this is the interesting thing. Okay, so at a trivial level, yes, we can run this. We can just set up we can configure a random pure state like this. It's got some state vector, and then we can just apply circuit C to S. We get a different thing, a different state vector that's just obtained by applying this matrix to this state. But of course, an actual quantum computer, if you were interfacing with an actual quantum computer, you wouldn't be able to do this, right? Because this QDS object is not accessible. So what you would actually have is a measurement that would take place on one or more of these wires. So that's the next thing we need to add. So we'd have to say quantum measurement operator, and we need to pick a measurement. So let's do a computation, the simplest case, which is just a computational basis measurement, and let's apply that to qubit 2, to wire 2. So then we add the measurement right at the end, and so now we have a nice computational basis measurement gate there. And again, our operator changes a little bit. And if we do the same thing, so we have so we apply circuit C to state S. Now we don't get a quantum discrete state object. We get this abstract quantum measurement object. So now if we say simulated measurement, okay, not very excitingly, we got back ket1. So obviously there are 2 measurement outcomes, ket0, ket1. We could do 100 simulated measurements, and we can see we get mostly ket1s with the occasional ket0.
Just say counts of that. Just say counts on that thing.
Well, actually, we could do better than that. We could say probabilities, and we can see it. So 83% of the time we're going to get ket1, and if we wanted to do, we can say like probability plot, and we can get a nice probability plot of that. And so we could do a more interesting measurement. So like if instead of m being sort of arity 1, we could make it a 2 arity thing. So now we're doing a computational basis measurement across wires 1 and 2. So now our operator changes again. Let's do the same thing. Let's measure that. Okay, now you can see we've got 4 measurement outcomes kept 1, 2, 3, 0, 1, 2, and 3. Now our probabilities are going to be a little bit more interesting.
Wait a minute, I don't understand. What is ket? Is ket 3 1 1? I mean, why isn't ket 3 written as some?
Yeah, so ket 3 is ket 1 tensor product ket 1.
Okay, but why is it written as ket 3 then?
Right. So this is
because it isn't a pure state anymore. It's a measured state, which doesn't have a good notation in quantum mechanics.
Well, exactly, yes, which is right. That's exactly right. So actually, if we see internally how this measurement works, is so we can say measure outcomes. So those are the named outcomes, but the actual hang on, wait. So if we say state association, I guess that's the key thing, right? So internally, what this measurement is an association mapping names of the measurement outcomes onto QDSs. Some of which will be pure, some of which will be mixed in general. And so it's these quantum discrete states that are the actual measurement outcomes. And this ket notation is just a way of denoting which QDSs were measured. So in fact, what we really want to do is not say simulated measurement, but simulated state measurement. And okay, this will take a little bit long. Oh, sorry, it's misspelled measurement. So we get a collection of quantum discrete states that are the outcomes of those measurements.
Okay, but so I don't quite understand why the keys in the measured results aren't just those quantum discrete states, as opposed to these made up kets with random numbers in them.
Well, so the underlying point is that the measurement, okay, when you perform a quantum measurement, the only information you're receiving back are eigenvalues, right? Eigenvalues of the measurement operator. So in this particular case, m, our measurement operator, happens to have 4 eigenvalues that are 0, 1, 2, 3, and so those are the ket.
Wait, where did the 0, 1, 2, 3 come from?
What do you mean? Those are the defaultly chosen eigenvalues of our measurement. We could make them different if we wanted to. So by default it would be 0, 1, 2, 3 because it's a 2-qubit measurement. But we can make them purely abstract. We could have x, y, z, w if we wanted.
Okay, let me understand this. So you're saying, so what I was saying is the sort of naturally occurring eigenvalues are just those things that you had down below, the quantum discrete states and so on. You are saying you can map those eigenvalues to some, I mean, this is called human, human is the consumer of the measurement. And they're saying, when the measurement device is in this state, I'm going to call it that. Is that what you're basically saying here?
Right. So in general, when you talk about performing a measurement, either in quantum mechanics or in quantum information theory, you, at least in my experience, you don't actually want the state. You want some kind of semantic interpretation of the measurement or the state of the measurement apparatus, right? You want to know, was this spin up or spin down? You don't want to know, you don't want to know the complicated mixed state that was the measurement outcome.
Well, that's an interesting claim. I mean, that's actually interesting with respect to our sort of way of thinking about the measurement process.
Right.
So you're saying, yeah, it's always good to operationalize these things. Okay, in any case, let's go back to our original question, which was, you've got, okay, so your few moments with your quantum computer, you feed in that circuit specification, you say, go run it 100 times. And it's going to generate a plot that looks just the same as the plot you just got.
Right, exactly.
Okay, so I want my quantum computer to impress me. What should I have it do to impress me? What should I have it do that you grinding here is going to take minutes for your computer to do the thing that a quantum computer is going to be able to do lickety-split?
Yeah, it's an interesting question. I mean, so in the circuit representation, the canonical example of something that quantum circuits can do much better than classical ones is Fourier transforms,
Mm-hmm.
That's the heart of Shor's algorithm and things like this. So probably what you would want is some kind of quantum circuit that contained lots of Hadamard gates, or even better, lots of multi-qubit quantum Fourier transforms.
Okay, so let's, by the way, save your notebook, Jonathan, before you lose all the stuff. And we could put it in the publicly shared, well, go ahead, quantum circuit test 01 or something. Yeah, whatever you call it. Okay, so build me up a quantum Fourier transform. Can you set up a small quantum Fourier transform here? And then let's look at the class of things that are like quantum Fourier transforms. Then we're going to do the NKS thing, the obvious NKS thing. So first of all, make a quantum Fourier transform, a small length 4, length 8 quantum Fourier transform.
Sure. Well, let's do length 4. Why not? So we can say Fourier 1, 2, 3, 4 or something. So now this has got some nice complicated matrix representation. And let's
can you decompose that into gates? Can you make that, for example, with our new, with your new gate compiler optimization thing? Can you write down that Fourier thing in terms of other gates?
It would be difficult. I mean, well, hang on. I doubt, because the quantum Fourier transform isn't really decomposable, as I understand. I mean, if we took an individual, I'm actually, now that you ask, I'm curious to see what would happen if I take an individual row of this and try to convert it into a ZX representation. Oh, sorry, no, I'd have to say. I suspect this will end up being indeterminate. Oh, no. Okay.
What the heck is that?
Had some difficulty. Okay, so it had some difficulty solving some part of it. The phase of this spider seems to be purely symbolic because solve couldn't work it out, but the other ones it managed to figure out. Okay,
well, it couldn't determine whether it was 0. I mean, by the way, you probably should put into that code some possible 0Q stuff for that purpose. Okay, but explain what on earth happened here.
Okay, so we just took a part of this matrix and tried to convert it into a ZX diagram, which I thought was not going to work, but actually it seems to have done. Yeah, so this is now a ZX diagram. We could, in principle, now feed this into a multi-way system because we have multi-way systems that know ZX diagram rules, and we could find a ZX diagram that was equivalent to it but simpler, and then convert it back into.
So I'm confused here. How come a ZX diagram could be done from a single row in this transition matrix?
Oh, so I'm cheating a bit. The quantum discrete operator to ZX diagram is not yet in the function repository. That's still in the review pipeline. So I was just testing with a single row whether we.
I see, like as if that was a state, a quantum state.
Right. Exactly. Which is why this diagram is completely linear, right? It's just got a collection of, it's just a tensor product of state spiders without any kind of interaction. Right.
So, Nick is actually suggesting that you redo this thing with the numeric version of the state vector.
Oh yeah, that's a good one. Yeah. Okay, that fails.
Okay, because it doesn't know something is a 0 over 0 somewhere.
Right.
Probably. Right. Okay, but let's come back to the bigger picture. So, you want this to run on a quantum computer. So any given quantum computer with any given technology has certain, primitive gates, just like a semiconductor computer has, NOR gates as its primitive gates. Mm-hmm. So, and the goal here, the goal of the compiler is to be able to take one of these transition matrices and turn it into something represented using those intrinsic gates. Is that a true statement?
Exactly. So internally, what the compiler, again, this is not yet in the function repository, but will be coming in the next few days. What the compiler does is it does this conversion of the operator to its ZX diagram form. Then it does the theorem proving. So then if you're trying to compile to a particular gate set, the form of the result, right? That it's a combination of spider, clusters of spiders that match certain patterns. So then what you're doing is you're doing a theorem proving problem, which is to show, to find a path from, the initial ZX diagram to the ZX diagram of the form you want. And then once you found that path and you know the final form, then you convert it back into operator form.
Okay, but so walk through for, the ZX diagram. So the ZX diagram is essentially given a matrix. There is a ZX diagram representation of that matrix. Is that a true statement?
Yes, yeah, or at least there will it may only be approximate, but there will be an approximate ZX diagram representation. Yeah,
and only approximate because the rotations in the ZX diagram that are defined by the ZX primitives might not perfectly match the rotations you need to get to those complex numbers. Is that right?
That's exactly right. But to within some epsilon, for any epsilon, you can find a ZX diagram that will approximate it.
But so is that like a continued fraction approximation to by rationals of a real number, or what? Is it the same idea?
I guess you could think of it like that. Yeah, in the sense that in general you might need an infinite Z, in the limit you might need some infinite ZX diagram to actually represent the circuit you care about. But for any given tolerance, you can represent it finitely.
So just so I understand, there are a bunch of theorems in number theory that will tell you things like, given, if I want to get to some particular number, well, actually, it's sort of obvious that to get to any specified real number, the decomposition in terms of other things, whether it's digits, other real numbers, whatever, might be infinite. That's the nature of real numbers, is that they pack an infinite amount of information. So in principle, to get a quantum circuit that has a particular real / complex number, a particular phase, for example, in it, might take an infinite number of discrete elements.
Right.
That's so weird.
Just to show this conversion for a slightly more non-trivial example, this is one of the documentation examples from the ZX diagram code. So if I take this diagram, this is corresponding labeled graph. This is a slightly more sophisticated tensor network. And then we could just say, convert that into, I guess, we want matrix form rather than operator form. And this would be the corresponding matrix form. And then we could, obviously, that can then be converted back into a discrete operator.
Okay, so I mean, the way I should think about this, by the way, what is the meaning of red versus green in the ZX diagram?
Right. So the green spiders, these are the Z spiders. These are the generalizations of rotations around the Z axis on the Bloch sphere. The red ones are the X spiders, which are generalizations of rotations around the X axis of the Bloch sphere. And so you need both in order to have a universal calculus.
Okay. By the way, just because I'm so persnickety about these things, it really would seem useful to have the graphic design group try and suggest slightly different reds and greens here.
Yes,
I know.
I know. Well, okay. I should justify this by saying that when we wrote the ZX diagram code, I wasn't expecting it to be part of a QC framework.
Well, I understand, right? And traditionally, those things probably are red and green. But we note to somebody taking notes. Let's get this recolored.
Yes.
But just to understand the interpretation of this, so in the ZX diagram, the fact that it has 4 legs tells me that there are 2 to the 4. It's a 2 to the what size is the matrix that I'm getting out here? Is it a
so this would be this is a 4x4, because this has so that you have 2 inputs.
I see, 2 incoming, 2 outgoing. So each one is like a qubit. And
exactly.
Right. And so that's a 4x4 matrix.
Right. And there is actually a generalization of so this hasn't been implemented yet, and I'm not going to, it won't be implemented for the first pass of the QC framework, but there is actually a generalization of the ZX calculus due to Hani Wang that came out recently that works for arbitrary dimension qubits. So in a future version of the framework, we'll be able to support that. But as conventionally formulated, it only works on qubits.
What's the relationship? I mean, naive question, but I mean the X and Z rotations, are they like the Pauli matrices? Those pieces of the Pauli matrix story?
Yeah, no, exactly. Yeah.
Okay.
They are generalizations of the Pauli X and Pauli Z operators.
And so then for the higher spin case, which is what you're talking about, you are dealing with the whatever the heck those are. Oh gosh, those are they D matrices? What are the generalizations of the Pauli matrices? There's a
So I don't know. I know that this paper exists and it came out a couple of weeks ago. I haven't actually read it yet.
Okay, well, I think it's the different representation of the rotation group, and I think it all probably wraps around these Wigner D matrices and things, or D. That would be my guess, at least.
That sounds very plausible. Yeah.
Okay.
But
anyway,
yeah, so internally, essentially, what the Z and X spiders are okay. So if we get if we say X comma pi over 6 or something. Wait. Sorry, X rotation. So that's essentially what the what the X spider is. That's what the Z spider is for for some given phase. And if we take it for the case where it's pi equal where the phase is equal to pi, I believe we should get the same as the Pauli matrices, or if we did X rotation.
Okay. By the way, Nick is making a comment that the last time he checked, matrix dimension was actually wrong in make ZX diagram. There shouldn't be those zeros there.
Oh, in the matrix form or the matrix dimension? In the matrix form, yes, there is a bug which has been fixed.
Okay. Are we still seeing the bug here or not?
In the make ZX diagram code, you are. In the quantum computing version, which has QDS to ZX diagram, I think it's fixed.
So explain to me something else. In this ZX diagram, what is the relationship between a ZX diagram and a spin network?
Well, in a sense, they are. You could think of a ZX diagram as being an instance of a spin network. They are both tensor networks with the same essential formalism, right? I mean, a spin network in the most general sense is just a multilinear function between representations of matrix groups, which is what a ZX diagram is.
Although, is there perhaps a dual character to it? As in, if I'm understanding this ZX diagram, the matrices, now I'm a little bit confused. I'm wondering whether in the spin network case, it's the edges of the spin network that are supposed to represent spins, and it is the vertices of the spin network that represent the kind of J1 equals J2 plus J3 type thing, the intertwining of the spins. Is that the same way around here? Is that it must be the same way around, because the outgoing legs here are like qubits.
Yes, right, yeah, yes, no, you're right, yes.
I'm right that the edges represent spins.
I don't know about spins, but it's certainly the case that in this instance, the vertices are the irreducible representations and the edges are the intertwiners, which is the opposite way around to a spin network.
Okay. Sorry, say that again. Let me just clarify that. What
So in a sense, each vertex is an irreducible representation of a matrix group.
Yep.
And each edge is an intertwiner between those representations of the vertex representations adjacent to that edge.
Okay. So
as I understand, whereas I've forgotten that, but yes, you're right. I think in a spin network, it is the other way around, isn't it? It's the edges of the irreducible representations.
Yes.
I get confused. Yes.
Right, but I mean then all these results about spin networks, like for example, if you have a big floppy ZX diagram, what does it like? Can you look at, for example, the extremal, like you can in spin networks, you can find classical gravity and things from spin networks and so on. What happens to a big ZX diagram?
Right. Well, we don't know. I think that's one of the things we want to figure out.
Okay, but so if we just make a big ZX diagram, so I was thinking we just make a big spin network, right? A big spin network has certain constraints, and the constraints do not determine the spin network. There are many spin networks consistent with those constraints, but the extremization for classical gravity is to look at some kind of extremal point with respect to all of the possible undetermined pieces of that spin network.
Right.
And so the question would be, what's the analogous thing to do here? I mean, in the case of a spin network, what one I think is saying is there is a certain topological structure of the spin network, but then the actual, oh, what is one saying? The actual, it's like the orientation of the spins is undetermined in some
Right.
sense, but they have certain constraints from the fact that they exist at vertices of the spin network. Any three spins have to be in some relationship because they intersect at that vertex in the spin network. Then the question is, what set of possible, so let's say we've got a big spin network and it's got 1,000 edges in it. That means we've got 1,000 spins, but we've got a whole set of equations effectively that are relationships between those spins. But there are many possible solutions to those equations. But the claim is that if we look at that there is an extremal point in that space of possible solutions, there's some kind of stationary point that corresponds to classical gravity, is I believe the claim.
Right. So,
there's go ahead. Yeah.
The ZX case is a little bit different in the sense that it's okay. So ordinarily, one is not considering ZX diagrams immersed in a manifold,
right?
And so the triangle inequality doesn't necessarily hold. And also, the other rule, which as I understand is fermion conservation, there isn't an analog of that in for a pure. Because I mean, these are just matrices. These are just arbitrary matrices. There's no such constraint.
Right, but for a given ZX diagram, a given big ZX diagram, well, you're saying any given ZX diagram just represents a particular matrix.
Exactly. So I can just throw down arbitrary vertices with arbitrary phases and connect them together in an arbitrary way, and what I will get is a valid matrix. It may or may not be unitary. It may or may not be Hermitian. Whatever, but it will be a matrix.
Okay. Whereas you're saying in the spin network case, the thing may not satisfy the triangle inequality. It may have J3 is greater than J1 plus J2, which means that its weight in the but this must have weights as well, right? The red thing is like a Pauli matrix, which has actual weights in it, doesn't it?
Yes, but so all I'm saying is that if you were to do this, you would need additional constraints that are not purely specified by the ZX calculus. You would have to say, I want my, I only want to have unitary representations or something. It's not sufficient just to have a ZX. The rules of the ZX calculus don't provide any non-trivial constraints.
Well, that's partly because there's nothing in the spin network case. If I had a spin network which was this shape, I would still have arbitrary labels of the J sub I, the values of the spins on each edge.
Right.
Whereas here, which is an undetermined piece in the whole thing, whereas what you're saying here is that everything is determined. The diagram determines everything. The diagram ultimately just determines the matrix.
Exactly, yeah.
Whereas in the spin network case, all one is saying from the structure of the spin network is there's a whole range of possible, collections of J sub I consistent with that structure. Then we can ask questions. Okay, so fair enough. But given a particular set of J sub I's, every vertex in the spin network has an associated 3J symbol, which gives its actual value, I think.
Right.
So then it too, given, okay, so it has labeled edges. Given those labeled edges, it's going to give, it won't be quite a number. It will be in general a tensor, if I'm not mistaken.
Mm-hmm. Yeah, I think
because it has it has legs hanging out just like this one does. Right. Okay, fair enough.
But yeah, so the place where this gets really interesting, and I think I've mentioned this before, but it maybe is worth saying again. This whole business of immersing spin networks into manifolds, right? We have a way of doing that in the context of the physics formalism for ZX diagrams, because what we can do is we could take a ZX diagram and immerse it in a hypergraph. Right. So what we do is we just take I'm gonna take a Wolfram Model hypergraph state, but I'm gonna arbitrarily specify that certain vertices are ZX generators and certain hyperedges are really ZX edges. And then in order for that thing to have a reasonable continuum approximation, the ZX diagram must satisfy the triangle inequality. And then you have some rules that you define on this composite immersed object which combine the ZX calculus rules and the rules for some, say a relativistically invariant Wolfram model system.
Mm-hmm.
And then you have what has not yet been really developed in the categorical quantum mechanics community, which is that you have a spatially extended variant of ZX calculus, kind of a first step towards categorical quantum field theory.
Right. But so, I mean, the big picture there, you might call it a painted Wolfram model, so to speak. That is, it is not a pure hypergraph. It's a hypergraph which has, red and green labels on hyperedges. Is that a true statement?
Right. So already when we evolve one of these ZX diagrams as a multi-way system, we are essentially treating it as a painted, or as we called it, just a labeled Wolfram model system. Right. So it's just, the rules of the ZX calculus are graph rewriting rules. It's just that they use a bit more information than the pure Wolfram model case, because you have to care about, what the phases are and things like that.
Right. But the ZX calculus is ultimately a set of essentially identities between combinations of matrices that are represented in graphical form. Is that a true statement?
Yeah, exactly.
And so,
so the interesting thing is, if we could derive a set of rewriting rules, because essentially what you want to know is, like, we have the rules of a Wolfram model, we have the rules of ZX calculus, but suppose this were now embedded in a manifold like hypergraph. So you have like two ZX spiders, but they're separated by a spatial vertex. Then you have to have rules that express the compatibility between the spatial vertices and the spiders. But then what you can do is you could have those rules set up in such a way that the information propagation through the ZX diagram effectively has a finite speed of light, which they don't,
yes.
Which isn't true in a standard in ordinary ZX calculus. And then you have the situation where actually the quantum mechanics of the diagram is affected by the geometry of the spacetime, which starts to get kind of interesting.
Yeah, I agree.
But
just zooming out a little bit to understand this matrix decomposition business. So the claim is, if we just thought about, and maybe I've just been sort of asleep in too much of the whole tensor network world, development. I mean, is there a general way? So you've got a tensor and you're decomposing that tensor in some way, and there is a diagrammatic calculus then that represents identities between different representations of the tensor. What is the general way of thinking about that? Is that a whole field of, is that what tensor networks kind of are doing and I haven't been paying attention, or I haven't seen a diagrammatic formalism. Even at the level of basic matrix decompositions from the 1960s and so on, are there diagrammatic versions of those?
Yes, yeah, and so this is what the whole field of string diagram rewriting in category theory has kind of been about, right? So ZX diagrams are.
I thought there was a whole field that I didn't know anything about. Okay, go ahead. Talk about that.
So ZX diagrams are a particular example of what are called string diagrams, right? So a string diagram is a way of representing a monoidal category, or specifically a symmetric monoidal category, as by means of a tensor network, right? So obviously, monoidal categories are categories that have some generalization of a tensor product structure. They have the monoidal structure. And so a string diagram is a way of representing such a category. So in a string diagram, just like in the ZX calculus, the idea is that you have generators, which are just nodes, and you have edges, which are just edges. And in string diagrams, they're often called wires. And each time whenever you have sequential composition of wires, that corresponds to essentially some generalization of matrix multiplication. And where you have parallel sort of stacking of wires, that corresponds to a tensor product or a monoidal product. And so then the argument is that an arbitrary decomposition of the tensor into generators can be represented as a string diagram. And within that, there's a whole field called graphical linear algebra, GLA, which is all about taking matrices and linear transformations and things and expressing them by means of string diagrams.
So again, very naive question. You take a number and there are representations like a digit representation, a continued fraction representation, things like that. And what you're saying, you take a matrix or a tensor, and in a sense, what you need to do for the quantum information case is you're decomposing an arbitrary complex unitary matrix or something into pieces that can be represented by these discrete set of possible gates. Just like you take an arbitrary real number and you're saying I'm going to have powers of 10 or something representing successive digits and so on.
Right.
What is the analogous thing? And maybe this is for tensors, you're saying that in the string diagram case, you've got tensor product and you've got matrix product, so to speak. You've got outer product and inner product in a sense.
Yeah,
and
exactly.
you're
The analog of like the base of your digit sequence representation or something that is essentially given by the set of generators of the string diagram, right? So for ZX calculus string diagrams, those are the Z and X spiders, and so they are expressively universal because we know that any quantum circuit can be represented by composing them in a string diagram.
Okay, but so you're saying, I mean, what's the theorem? Like for numbers, we know that you can have, I mean, it's a slightly complicated thing. You can have, if it's an integer as the base, then there's a unique representation. If it's an algebraic number, there's a non-unique representation, et cetera, et cetera, et cetera. And it's probably obvious that any transcendental number will also work, but will not in general be unique. But so for matrices, for tensors, what are the possible bases?
Right. I mean, so yeah. So this is all about what generators can you have if for your string diagram.
Yes. Right. So in other words, what gates, which relates back to the original question of what gates do you need to make a universal quantum circuit?
Right.
If the definition of a universal quantum circuit is you can make any unitary matrix, which is, by the way, a cheat, because as we've been discussing, the arbitrary unitary matrix is arbitrary precision, and you need an infinite number of gates to achieve that.
Right.
So then let's ask the question, what does it actually mean to be universal? In other words, given that, in the case of Turing machines, we have a very well-defined base. So if what we say is, I suppose we have to base it, I think that's what David Deutsch, for example, originally did, to base it in quantum Turing machines. To say, can you emulate a quantum Turing machine, which is not the same statement as, can you, if you're doing chemical reaction with an arbitrary, Schrodinger equation with solving it with arbitrary precision, complex numbers, that's a different question. And I mean, I don't even know what's known about, people have claimed that there's universality with respect to simulation, but I wonder whether that's even true.
Right.
I mean, I wonder what on earth that means, because in a sense, to get, to set up the initial conditions, because, your typical chemical, computation, I cannot believe that if you give finite precision input, that it will give finite precision output if you solve the equations completely. So, okay, all right, but let's come back.
Just before I forget, just as a visual aid, sorry, this is what I was this field of graphical linear algebra. This is kind of what it looks like. This is
lovely.
A diagrammatic representation of a matrix. So yeah, there are.
Wait. How does that work? Back up. How does that work? So this matrix has two indices. Where's the input indices? We don't know. It's on the left or the right.
I think it's going left to right. That's the convention.
Okay, so this is some kind of what this is saying. What is this? Is this some kind of permuting thing or what?
Yeah. No. So in a sense, you have for any product.
Wait a minute. That thing is just a complete, mixing of everything, right? That diagram. If you made that, would be like the it's a complete graph, isn't it? It's a K, whatever. It's that's K22, and it would be K33 if it was the 3x3 matrix, wouldn't it?
Well, that particular one is a complete graph, but I mean, like these.
If it's full of zeros, it might not be a complete graph. Is that what you're saying? Because that looked like a complete graph as well, the one you just had above.
But this
thing there.
That also. Wait, that's not bipartite complete.
No, it's not, because it's got more tentacles on the output. But in other words, to represent an arbitrary matrix, we can do it by just labeling, by just saying,
I should add,
Actually,
I don't know that much about graphical linear algebra. I know it's a field, and I know it's something I've been meaning to learn. But
right. Okay. Well, fair enough. Fair enough. But okay. So, but that's interesting. All right. So then,
yeah, so as one thing I do know is that there's this general rule that there's so the category of matrices. Okay, so a bit like the category of finite dimensional Hilbert spaces. We know FD Hilb is some symmetric monoidal category. The category of matrices we know is this prop, right? It's a product and permuting category. And so there's a rule that if you can produce a prop of diagrams, prop category of essentially of generators, and you can define a faithful functor from that prop to the prop of matrices, then that forms a valid diagrammatic calculus for matrix algebra. And so this is one example of diagrammatic calculus for one particular matrix prop.
So what I can imagine is something like the Fourier transform matrix, the FFT matrix, would be an interesting graph. What is that? It's some kind of butterfly graph type thing. That would be presumably the analog. I mean, that's a place where there is a known, well-known relationship between a graph and a matrix.
Right.
Okay, okay, there's a question on our live stream, and there are a bunch of interesting questions here, but there's a question here from SL8 asking, fundamentally, why are ZX diagrams helpful in understanding quantum mechanics? What is the fundamental reason?
Okay, I mean, do we mean understanding quantum mechanics in a general sense, or understanding quantum mechanics from the point of view of the physics project?
Well, why don't you start with it at a general level, and then home in? I mean, I'm curious to know what the kind of succinct version of that is. Sell ZX calculus.
Okay, so from my perspective, the thing that is useful about ZX calculus, over the sort of traditional way of thinking about quantum mechanics in terms of Hilbert spaces and things, is that it is much closer to the computational foundations of quantum mechanics than the standard Hilbert space picture, right? So in the standard Hilbert space picture, you think of states as being the fundamental structure, right? You think of vectors in some Hilbert space as being the thing that's actually interesting, and then you consider operators acting on those Hilbert spaces. In ZX calculus and in categorical quantum mechanics more generally, but ZX calculus particularly, you think of processes as being the fundamental object of study, and the states are somehow secondary, right? So that's essentially what these string diagrams are giving you, right? Each one of these edges is a process. It's telling you, and the ZX calculus are a collection of rules for how these processes compose in sequence and in parallel. And so in a sense, it's telling you that there are only really two fundamental operations of quantum mechanics. You have a bunch of quantum processes, and they either compose in sequence or they compose in parallel. And those compositions have some algebraic properties, and those algebraic properties are what the ZX calculus is representing. And that view, that as that process-centric view versus the state-centric view, is a different way of thinking about quantum mechanics that is somehow much closer to the computational picture. That would be my
right. So this is actually historically. Here's the thing that I've been meaning to understand: what is the relationship between process algebra and this whole categorical quantum mechanics ZX calculus thing?
Right. So I don't know historically what the connection is. I just don't know that much about the history of process algebras. But I mean, so ZX calculus is a process algebra, right? It's just an algebra for quantum processes. But process algebras are another, I assume, are a kind of more general way of reasoning about
right. I mean, what's interesting about this, okay, from a language design point of view, we understand, in functional composition, we understand very clearly sequential, serial application of functions. We don't understand as well parallel application of functions. Mm-hmm. And I guess my question would be, if you were going to turn a piece of ZX calculus into language design, because that's my obsession, what would it, I think the answer is going to wind up being the thing that I've been meaning to build for like 40 years, which is, just like you have infix operators, right? Where you say A blob B, where blob is an operator that stands between A and B and makes you, f of A B.
Yeah, it's higher arity infixes.
Well, I wonder. You see, I've always thought that there should be a thing that I was calling long ago a graphics operator. In other words, that what's really happening is, instead of it being the case, like in a what's really happening is that the arguments are being picked up. I mean, that is what's happening in these pictures and these ones you were showing before about some string, this string diagrams and so on. Is, if I'm not mistaken, you're describing the connection of arguments by a graph rather than by something which would be written down as a standard kind of textual program. Is that right? Or am I confused?
Exactly. But my point is that each of these generators you can think of as being like an infix operator, just where the number, the left-hand side, the number of fixes on the left-hand side or the right-hand side is, can vary.
Yes, I agree. But the issue then is, if we were going to make, naive kind of thing, if we were going to say, and gosh, I meant to do this decades ago, something, in fact, we even have a prototype of this. We had a prototype of this in the early 90s, of a thing where you could draw a diagram as a graph. Every node of the graph is a function. And then the diagram can be evaluated as some full form expression. Because normally our expressions are trees. But the whole point of these things is that they're essentially sharing, more like a DAG. They're sharing pieces of there are shared variables, so to speak, in these things.
Right. What's essentially happening is that, my personal take, and I'm not a language designer, so this may be wrong, but essentially, I think mathematical notation has been constrained to be essentially one-dimensional for historical reasons, and that's enforced this view of expressions as being trees. And what string diagrams and these more general kind of graphical algebras are allowing us to reason about are cases of mathematical notation which are not strictly one-dimensional, and therefore in which you, as I say, you have infix operators with kind of variable arity.
Exactly. Yeah, you're recapitulating my thinking from the mid-1980s here, and which came back again in the mid-1990s when we first implemented two-dimensional input in Wolfram language. And that's when I started thinking about graphical diagrammatic input. And then we had an initiative, which I must admit that I killed, which was a Roger Germanson initiative to basically implement graphical languages directly in the system. And the reason I killed it was because, I looked at the different graphical languages. I knew the different graphical languages that existed. They're all rather different, and they all only go a certain distance. Like, yes, there are things that it's useful to draw the circuit diagram for, and that's the best representation. Yes, it's things where it's useful to draw the Feynman diagram. But after not very long, you're like, oh my gosh, I can't understand this picture. Just give me some, textual representation to work with. As a way of the human inputting things. But of course, that was before the physics project, where So I have to. Although we don't expect humans to be drawing the hypergraphs.
Right.
What did we just generate here? What's that?
Generated a piece of nonsense because there we go. So I'm just showing. So although this is this is morally a in this case a two-dimensional diagram, we can flatten the thing out into essentially a product of individual generators, which is what the operator form of a ZX diagram is giving you.
Do the parentheses matter?
No.
It's associative in some way. Okay.
It's a product, so it has to be associative.
And so then the arrows are just telling you how to match the indices up.
Exactly. Yeah.
Okay. Eli on the live stream is asking, about explaining the importance of ZX calculus in the framework of the physics project. You want to just say something quickly about that?
All right, yeah. So for that, that's a slightly more abstract direction. So, well, okay, obviously, one aspect is really obvious, which is that, ZX calculus is kind of telling one that it's possible to do quantum mechanics just using graph rewriting, and that's obviously of immediate interest to the physics project. But there's a deeper reason for it, which is that ZX calculus works because of the algebraic properties of finite dimensional Hilbert spaces, which you are essentially recapturing using these string diagrams, right? It works because we have a monoidal structure, which means that we can stack generators next to each other and apply edges in parallel. It has a compact structure, which means that we can take duals of objects. It has a dagger structure, which means that we can reverse edges, which is like taking a Hermitian adjoint and so on. And the significance for the physics project was that if you construct a multi-way system of these ZX diagrams using ZX calculus, it turns out rather interestingly that the multi-way system inherits those algebraic properties, that the category of multi-way systems also has the same algebraic properties as the category of ZX diagrams. In fact, they are both props from which there exists a faithful functor from multi-way systems to ZX diagrams and back again. And the reason for that is that in a multi-way system, we can take monoidal products because we can essentially take disjoint unions of rules. We can take Hermitian. We have a dagger structure because we can reverse the direction of the rules. We can reverse the evolution arrows in the multi-way evolution graph. We can even take duals because we can, if we have an object in the in the multi-way evolution graph that is a hypergraph, we can take the dual of that. And that also satisfies the requisite algebraic properties. So somehow the multi-way systems inherit the same algebraic structure as the ZX diagrams, and that gives one a formal way of proving that the multi-way systems are in fact a valid context in which to do quantum mechanics, because they form a compact closed dagger symmetric monoidal category, which is something that I think would have been quite difficult to prove had we not had the ZX diagrams there as kind of the framework for it.
Right. So, okay, let's zoom out and come back to our original question. I want to see quantum computers sing and dance in some interesting way here. Right now, we're not seeing a lot of singing and dancing. I mean, in other words, so we were starting to look at quantum Fourier transforms, and we were looking at, where do we get that? We had our quantum Fourier transform there. But that isn't really, there's nothing particularly quantum about that. That's just isn't that just a Fourier matrix? Isn't that just a...
In a sense, yes. I mean, it's a discrete Fourier transform, but where the matrix is obviously not diagonal, so it's quantum mechanical in that strict sense. But
take that matrix, and if I take the vector, 1 0 0 whatever, right? In what sense does that matrix, when applied to that vector, give the Fourier transform of that vector? It's giving the Fourier transform of the logarithm of that vector in some sense, isn't it?
Mm-hmm. Right.
So can we see that actually work so that matrix is the matrix that is being applied. We've got all possible superpositions. What is this? This is this is a, what is this thing? This was a...
Well, you asked for arity 4, so this is a 16 by 16.
Okay, fine. Okay, so this is 4 qubits. And what this should be doing is giving us, given that we have a superposition coming in, it is going to do the Fourier transform of each individual piece and add up those, the things with whatever superposition came in and give us back the resulting amplitude vector. Is that correct?
Right.
The resulting state vector. Okay, and then the question is, how do we decompose this in terms of gates? So, for example, in Shor's algorithm, if I understand correctly, one of the key parts is decomposing this. I mean, how many gates do you need to do a Fourier transform of a certain size?
Right.
So what's the answer? I mean, in other words, to do a Fourier transform, again, I'm now completely confused, because how do you do... These Fourier transforms have arbitrary precision, don't they?
Mhm.
So don't you need to have some rotation that is precisely the rotation needed for that arity of Fourier transform to be able to do this with a finite number of gates?
Well, yeah, I mean, but this is true of any quantum compilation problem, as I say. I mean, it's only ever inexact, right? You can only ever compile a circuit to a gate set to within some epsilon.
Okay, but so in this particular case, can we see the example? I mean, in Shor's algorithm, for example, what what is the quantum computational complexity of this Fourier transform?
Right, right. So obviously, again, as with any of these compilation problems, it depends on what gate set you're actually using.
Mm-hmm.
So in general, what you would do is you would have, okay, so like for a 3-qubit, okay, so okay, for an n-qubit quantum Fourier transform, what you would have is you would have a Hadamard gate and then a collection of phase change gates. I think you would have one fewer than the number of qubits, and then on the next Y you'd have a Hadamard gate and then another collection of phase change gates and so on, and you'd queue those up, and that would give you a simulation of the quantum Fourier transform.
Okay, so but the key result that everybody says, oh my gosh, it might break, factoring as a means of doing cryptography or everything. The key result is that there is in the end, if I'm understanding correctly, is that I mean, normally Fourier transforms are, n log 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 n, whatever it is, time things, classically. Mm-hmm. What is the corresponding result based on quantum gates? And now I'm in this formulation, I'm somewhat confused. I mean, so the point is, it's just essentially a Boolean network, a quantum Boolean network, and you are simply doing the Fourier transform by flowing through that network, just as you could do it with matrix multiplications with these butterfly networks and things like that for the fast Fourier transform. But mm-hmm. somehow this is much faster in this case.
Right.
And I'm just trying to characterize, and part of the reason it's faster is because what's happening is it's got an amplitude for many different possible inputs, and the quantum Fourier transform is doing the Fourier transform somehow all of those together, rather than doing one at a time. But how do we see that? I mean, in other words, we should be able to see, oh, we can do this quantum Fourier transform with this modest number of gates. Whereas if we were try to think about how to do this classically, we couldn't have the superposition as input. So we would have to do each piece separately. Is that the idea?
Right, right. Yeah. So in the naive case, to do a discrete Fourier transform would require on the order of, for 2 to the n amplitudes, you would need
on the order of 2 to the n gates, 2 to the n log log, whatever it is.
Right. So with Hadamard and phase change, you need only n squared. And there are other algorithms for different gate sets that need only n log n.
Okay. It'd be nice to be able to see that with this framework. Is that plausible?
Yes. I mean, yeah, but we'd have to actually construct the circuit. So I mean, like, okay, let me. Here's an example. So I just looked this up. So the 4-qubit quantum Fourier transform. This is its simulation using Hadamard and phase change. So
okay. So then you should be able to make a picture like this for an n cube, 2 to the n qubit thing with Hadamard and phase change, for example. You should be able to, those have two, that's a pi over 4 and a pi over 2. So you can obviously get the pi over 2 by a pair of, oh no, I'm seeing pi over 8, 4, 2. How far does it have to go? Do you have to have a phase change of pi over 2 to the n?
Yes.
Or something of pi over?
I think so, yeah.
Okay. All right. So, but we can clearly get that. I mean, this is cheating a little bit, because if we say we're locked into having only pi over 8 phase change, we just had to have a whole bunch of gates to do these things. In other words, in this case here, we will have to have, let's imagine that we're doing 2 to the n, we're doing n wires, then this is saying, okay, so then we might in general have to have n, our minimal phase change will be, let's say, 2 to the you know, 2 to the n, pi over 2 to the n minus 1, for example, let's say. That's the minimum phase change. So then, let's see.
Actually, sorry, I'm remembering something. I think I may even have had, sorry, excuse me one moment while I dig out.
Yeah.
I think in an old version of the documentation, we may have had a picture of this.
Am I being very confused, or isn't there a cheat going on here? In other words, in order to get, if you say I'm got pi over 2 to the n, I've got gates that do pi over 2 to the n phase changes. Am I being very confused? Or don't you need 2 to the n of those to do pi, to do a phase change of pi?
Yes, I think that's right.
So I don't understand how this works. The whole claim is that you don't need exponentially many gates.
Right, but the argument is that the phase change gate with arbitrary phase is
comes for free.
Sorry?
Comes for free. It's just one gate.
Yeah, well, so mathematically, the S gate or the T gate, which is what we're dealing with, those would count as a single gate.
So when you implement this with actual devices, do you get to do that? No, you don't.
That's the thing I don't know. I mean, so I'm hedging.
Well, I mean, it's right. Is it like, oh, you have this microwave cavity and you run it for longer or something, and it makes a bigger phase change or something?
Right. Sorry, I just realized instead of showing Qiskit's documentation, I could show our own documentation. So this is an old documentation page that I haven't updated with the new design, but this is showing this is a simulation of a 3-qubit quantum Fourier transform just using Hadamard phase change, and it's showing that if we did if we apply this circuit to some uniform superposition state, and we applied the built-in quantum Fourier transform, which is just the Fourier matrix, to the same state, we'd get the same answer.
Nice. Okay, so our original kind of NKS-ish question is: there's a picture. It has whatever it is, 7 gates in it, right? Mm-hmm. Okay, so I imagine enumerating all possible quantum circuits with and it matters then that you're going to the enumeration is going to get blown up by having arbitrary phase change. So let's imagine that we lock in a particular base primitive phase change,
right? Okay?
And we enumerate all possible circuits that have those, that have 4 gates, 5 gates, whatever it is, right? Mm-hmm. And now the question is, okay, so each one of those circuits is essentially a unitary matrix. We can ultimately represent it as a 2 to the n, as a unitary matrix of the kind that you've given there, right?
Right.
Yep. Okay. So given gates, we can get a unitary matrix. So now the question would be, if we were to, like, for example, here's an obvious kind of question. We could start, we've got unitary matrices. They correspond to, okay, here's the thing. Let's say we're visualizing each unitary matrix as an element of UN, unitary, Lie group. Yep. And imagine we have a visualization technique for UN. Okay. And imagine, let's say it's, I don't know. I don't know whether we have unimodular matrices or not, but let's say we had SU2 coming out of this. Then that's like coloring a sphere. In other words, that matrix is representing a rotation from the North Pole. Each such matrix represents a point on the sphere. True statement?
Mm-hmm. Right.
Okay, so you see where I'm going to go with this. So the question then is, as you increase that, so you've got a sphere, represents SU2, represents a collection of those matrices. And I guess we can just think about these, the two output, lat long output matrices, so to speak. So now my question is, as we add more gates in, what happens? We're coloring the sphere. we're putting down points on the sphere that correspond to the possible transformations made by the matrices generated by some collection of gates. So my question is, how does the sphere get filled in? So presumably the claim would be, if it's a universal set of quantum circuit elements, eventually the whole sphere is filled in, right? There exists a circuit that can get to any point on the sphere.
Right.
Okay, so my question is, what are the easy points on the sphere versus the not so easy points?
Mm-hmm. Yeah, that's an interesting question.
Right, and so one would suspect that the thing will fill in. I mean, I'm thinking. So one way to.
And by the way, I should mention, just again from a purely design perspective, this isn't implemented yet, but there is a plan to introduce some functionality that would make it much easier to do this visualization, because so we already have a bunch of like decompositions for things in the QC. Like, here's an example. We could do a Schmidt decomposition of an arbitrary state, or you can do spectral decompositions and Weil decompositions and things like that. We are planning to allow you to do Clebsch-Gordon decomposition of operators for arbitrary numbers of dimensions, so essentially to compute the angular momentum coefficients in arbitrary numbers of dimensions for unitary groups of arbitrary order, which would let you actually visualize this.
Let me understand that claim. Okay, hold on. What are you saying there? So you're saying, what are you saying? You're saying we have an n qubit output, which we're thinking of as, let's say they're qubits. That's a bunch of spinor half particles, basically. That's a bunch of spinor halves. And you're saying, given a product of 5 spinor halves, there is a decomposition of those using Clebsch-Gordon coefficients in terms of single spinor half states. Is that what you're saying?
Exactly. Or I guess to think about it less physically, the decompositions are telling us the integrals of spherical harmonics, right?
Let me think about that. So your claim is the Clebsch-Gordon coefficient.
The coefficients, they are the expansion coefficients for products of spherical harmonics in terms of a single spherical harmonic.
Are they? Let me think about that. You're saying that you can compute the Clebsch-Gordon coefficients by using spherical harmonics as some kind of representation of this group, and then you reduce the problem of computing those recoupling coefficients to doing integrals of the spherical harmonics. Is that the claim?
Right, exactly. Which, I mean, that just follows from the fact that the spherical harmonics are orthonormal, so we can use them as a basis.
Right. Okay, but you're saying then.
So in effect, then, once we have functionality that does Clebsch-Gordon decomposition over an arbitrary unitary group, in effect, that will that will tell us the coordinates on the sphere.
Actually, what it tells us is we can write it as multiple. What is it telling us? We've got a product of a bunch of spins. Wait a minute. Usually what happens is you write, the product of a bunch of irreducible representations is a sum of irreducible representations, isn't it? It's a sum of pieces from different representations.
Right.
Like, naively, back in the very earthy, crunchy days of thinking about QCD millions of years ago, it's like the 3 representation that of SU3, which has quarks in it, 3 cross 3 bar or something is equal to 8 plus 1.
Right.
So that's the decomposition, is that those, in that case, spinor representations of SU3 are the product of 2 of those is an 8-dimensional representation plus a 1-dimensional representation.
Mm-hmm.
So I don't quite understand in this case, if we've got a bunch of qubits and we do a Clebsch-Gordon decomposition, aren't we going to get the equivalent of a spin, a spin 12 object or something, plus a spin 10 object plus or whatever.
Yes.
Okay.
But
Which is not, I mean, and then to visualize the spin 10 object, you need essentially the analog of a polarization vector, which is a polarization tensor for that object, I think.
right.
Right. So like for spinner half, for spin one, the polarization vector is a vector.
Mm-hmm.
For spin a half, we can get away with using a vector to represent the polarization direction and the spinor polarization direction.
Right.
And in the more general case, we need some kind of tensor to represent that. So
Mm-hmm.
I think it is not obvious how you do visualization of those higher dimensional cases, I think.
No, sure, but my point is simply that the angular momentum operators that you get give us a basis of this spherical tensor, right?
Yes.
And so if we yes, in general that will be higher dimensional, sure, but we can once we have that basis, we can project it onto stuff, right? There's stuff we can do once that basis exists.
Yeah, all right, fair enough. I mean, one thing you can certainly imagine doing is you can represent the different polarization states. You could represent by sort of the support of different spherical harmonics, the YLM, for a given, the polarization states correspond to the different M values in the YLM.
Right.
And so
right.
each YLM has a distribution on the sphere that, for a given L, each YLM, like the maximal M's of plus minus L are these long pointy orbitals, so to speak, as opposed to the more blobulous, orbitals for M equals 0 and so on.
Mm-hmm.
So I see. So I mean, we could sort of in some very chemical way, we could represent the different states there like that. But okay. But I mean, the fundamental question here is we're asking the question, given logic circuits, I don't even know how to do this for classical logic. Okay. So it is the case. I mean, I did this thing in NKS, actually. I remember doing this. For n input logic, if you have n inputs, one output, there are 2 to the 2 to the n possible Boolean functions. The question is, given a small number of gates, like a small number of NAND gates, of those 2 to the 2 to the n Boolean functions, which ones are easy to produce and which ones are not? And there is always a holdout of the hardest to produce Boolean function, if that makes sense.
Right.
Now, the question here is, I mean, I think in the case of Boolean functions, there's a distinct so what to that question. Except if you're designing a computer, then in principle, if you wanted to make opcodes for all these different Boolean functions, there'll be one that has the longest time delay because it has to go through the most layers of logic.
Right.
But I don't think anybody cares about that. The question is, in the quantum case, what's the analogous, then there will be some quantum function which is computable with that. Yeah, there'll be, in the case of the quantum case, we actually already know there could be an infinite number of gates needed to compute a given unitary matrix because of this problem about precise numbers.
Mm-hmm.
And so then the question is, as we home in on different unitary matrices, which ones require how many gates to produce them? But I mean, that's sort of an amusing question. It's definitely I mean, I'm trying to remember. Go ahead.
It's the same as the length of normal forms for a proposition, for a Boolean function, right? It's like, how long is the conjunctive normal form for some Boolean function?
Yes, that is. Well, it depends. I mean, that's two-level logic, right? Where you just have an and of an and of an or, so to speak. Whereas,
right, my point is that those there is for any universal classical logic gate set, right? There's a different normal form. So like ands and ors give you conjunctive, disjunctive normal form, but you can also, there's like algebraic normal form for XOR and things like that. And those are like different gate sets. And so what you're really asking is for a particular sort of normal form, what's the minimal normal form for an arbitrary Boolean function, which I know is that's definitely a question people have looked at.
Yes, I mean, I looked at this in NKS. I'm trying to look up what I actually did here.
Right.
And I mean, in the case of, I mean, I can tell you facts. Like, for example, XOR requires an exponentially large number of gates in DNF and CNF.
Mm-hmm.
I mean, that was an early result. It was an early lower bound result for Boolean circuits. And presumably in the quantum case, people have done the kind of lower bound, tried to do the lower bound results for particular functions that you might compute.
Yes, I think so. But it's obviously much wilder than it is for Boolean logic.
Right. I mean, I think
because like for Boolean functions, you've got things like the Quine-McCluskey algorithm, right? Which is like a, you know, there are well-defined algorithms for doing Boolean minimization, which are
well, actually, I mean, yes, I know this history because in the early versions of Mathematica, I wanted to have Boolean minimization. Okay, at the time, it was not possible to do it in reasonably short amounts of time. It was, you know, satisfiability is already NP complete, right? And in practice, Boolean minimization was also sort of exponentially hard. It became possible in the 90s. A bunch of algorithms were developed that go beyond the kind of prime implicant Quine-McCluskey type stuff that eventually managed to make it so that we can actually do pretty large Boolean minimization in very, very quickly. And it was I don't completely know how those algorithms work. Actually, would be, I mean, there's a program called Espresso, which is, I think, how we ultimately do it. But
right.
Let's see.
I remember what was it, 2 years ago, supervising Adela Deng's project of trying to do, you know, like explainable Boolean minimization. That was quite a fun.
Yes, right. Let's see. Oh yeah, and then I looked at this whole question about when you look at cellular automata and you look at n steps of cellular automaton evolution, what is the minimum size Boolean circuit, Boolean function that represents n steps of evolution of a given function, of a given cellular automaton? But I'm just okay, so the answer is I have a note here. Here, I'll send you the this is it's one of these ridiculous NKS book notes where it just states some random result, which took large amounts of effort to get. But here, there you can bring up that particular note. And this is some claim. Okay, 2 to the 2 to the n possible Boolean functions. Maximum number of terms, oh, in DNF is this. Okay. So this is the answer. This is for DNF, at least. This is the which functions are, yeah, so XOR is always the most difficult. Oh, that's interesting. So the reason for this, essentially, these functions are the ones that make the coloring of a Boolean hypercube maximally fragmented. So I wonder what the analog of that in the quantum case is. So that's like the prime implicant business for Boolean functions. That's saying in order to make the Boolean function you are trying to compute, in other words, each DNF piece is essentially laying down some kind of hyperplane in this hypercube. And so
I get it.
Right. So what's the analog of that in the quantum case?
Mm-hmm.
And that I rather suspect, well, I don't know. So okay, let's go back to the quantum situation here. You can get rid of my classical thing. Okay, but again, okay, I should wrap up fairly soon, but I'm just trying to understand this. What's an exciting thing we can get? Okay, so we want to compute something like a quantum Fourier transform. We're going to compile it into gates.
Right.
We do not expect that. We expect for any given n, we will have to separately do that compilation.
Mm-hmm.
Just as for sorting networks, or for that matter for FFT networks, there is in general a different network for each different value of n.
Right. And there may or may not be a general rule for how it factorizes.
Right. Well, we know that if we want the optimal network is a messy function, is a messy sort of computationally irreducible function of n.
Right.
That there may be a family that does that that matches some bound, like it's n log n less than or equal to n log n time. That there may be a family that's easy to describe, like a quick sorter or something like this, even though the optimal will be for given n might be smaller than that.
Right.
But okay, but so
I should mention, by the way, that there's another layer of complexity to this, which is that another class of problems that's of interest, particularly more recently in quantum information theory, is if we have a continuous time quantum evolution, like for an adiabatic quantum computer or a quantum annealing problem or something, and we want to simulate that to within a certain precision using a circuit, then you're doing both. You're essentially asking, I've got some continuous time problem, and I've got the circuit picture, which is a discrete time representation, and how well can I simulate one with the other?
Right. I mean, it's like asking. Well, it's like you've got an iterated map and you're comparing it with an ODE.
Right.
It's far from obvious it's going to work at all.
Right. So like in our...
Does it work, by the way, typically? I mean, for anything non-trivial? I mean, if you're simply having an adiabatic, if you're having a phase change, e to the IHT or something as a function of time, how on earth does that work with fixed, phase change gates?
Right. Let me try. Here's a Hamiltonian for some non-trivial quantum evolution. And so then if we wanted to get out, we can get out this arbitrary evolution. We can get out an evolution operator, which is now some symbolic function of the time parameter t.
Hold on. So that's the Hamiltonian. So the claim is there's an e to the IHT that is the matrix e to the IHT. Is that correct?
Exactly. Yeah. So when we call evolution operator, it's essentially solving the Schrodinger equation and giving you out a symbolic quantum discrete operator with dependence on t. But then we could also say, what is the evolution operator at a particular time? So we could say like, evolution operator 0.5. Oh, sorry, 0.5 or something. An actual numerical operator for that particular time. And
which is presumably the same thing as those interpolating functions. If you take the t in that thing with interpolating functions, it will just work.
Yeah.
Beautiful. Okay.
The point I'm making is, so implicitly, this Hamiltonian will have a time step to it. Now, by default, we tend to make the time step quite small. So in this case, it's 1 over 100, but we could make that whatever we liked. So in a sense, you can think about this. You can think about approximating this continuous time evolution by a bunch of discrete steps, each one of which will have an associated operator. And so what you want to do is construct a quantum circuit where you sort of like you subdivide the circuit into levels, one level for each time step, and you want to have the circuit up to that level approximate the evolution operator up to that time step, if that makes sense.
Well, why is this is a continuous time thing? What's this 1 over 100?
Right. So yeah, this is all of this is continuous time. So like obviously I could this. Oops, sorry. This can be some arbitrary real number. But when I then want to take that, so for the purpose of doing circuit compilation, which of course is kind of what the core of the framework is about, if I want to take this Hamiltonian and compile it into gates, into a circuit, I can't compile the straight up continuous time problem, right? I have to compile a discrete.
Okay, I get it. But then how do you approximate that matrix representation by what is the approximation method when you have that parameter step 1 over 100? How does that turn that matrix into something that you can actually, does that guarantee that matrix? I don't think it does. You've got an exponential Hamiltonian. I don't understand. I mean, in general, you're going to have a transcendental number that represents one of those phases. And that transcendental number might not have a finite number of gates to at least get the exact value.
Yeah, well, as I keep saying, quantum compilation is not about exact values, right? You can't do that in general.
But so the parameter step, why do you need the parameter step? If you're not going to be able to do exact compilation anyway, why not compute exactly the Hamiltonian, the e to the IHT, and then you're going to approximate it anyway. Why is there a reason to have the t?
So circuits don't have time dependence, right? A circuit is a
Yes.
one-shot thing. A
Yes.
Hamiltonian has time dependence.
Yes.
So what you want is a circuit which, so you want to have a circuit which like maybe divided up into 10 levels. And so after the first level.
Oh, I get it. Okay, I get it. You find the quantum. Actually, well, maybe you're saying that we should have the time value. The circuit is a whole sequence of gates, and if we cut it after some number of gates, we will get the continuous time values after one parameter step. After delta t time. Is that correct?
Right, exactly. So normally when people in QIT, when people talk about approximating a continuous time evolution with a quantum circuit, what they mean is exactly that, right? You have a circuit which is split up into levels, and where you could, in principle, end the computation after that. You could just stick a measurement in at any point, end the circuit at that level, and then you would have approximated the continuous time evolution up to some discrete time value.
Right. I'm still struggling though with kind of what the big actually another naive question, which you may not know either, but I haven't been following. What are the various technologies that actually implement these gates? I mean, I know there's Josephson junctions, there's ion traps, there's various optical things, and how does one make the translation between and maybe we have is there a qualitative way to think about what gates can be made with what technology, or is that a matter of
so there definitely is such a description. I just don't know what it is. I mean, I know that there are certain types of gates that are easier and harder to produce with certain, like I know that the set of gates that can easily be produced with ion traps is different to the set of gates that can easily be produced with optical systems, but I don't know the experimental literature well enough.
Right. And then ultimately there's a transporting a qubit around, which works very differently in these different technologies. I mean, in optical ones, obviously it's a photon that's doing it. In other ones, it is potentially a flux quantum, or it's a particle. Presumably an ion in the ion traps. That's presumably the point. Fair enough. I should learn this. I have not paid attention to this for way too long, and I need to go learn, exactly what these technologies are. I just don't know if one compares it with the semiconductor industry. There was a time when it was silicon, it was germanium, it was gallium arsenide, then it was silicon again. And
right.
And there are different, the CMOS technology, the MOS technology, et cetera, et cetera, et cetera. And each one had slightly different, in that case, again, gates that could be made with it. And people got used to the idea it doesn't really matter much. We got NANDs, we've got NORs, we've got.
Is it an urban legend that NAND was chosen essentially for engineering convenience?
It's actually NOR, isn't it, for CMOS?
Oh, is it NOR? I remember one was chosen over the other, essentially, because it was just easier to build the gates.
Yeah, it's easier to build a field effect transistor that does one rather than the other in that particular technology. Yes.
Right. Okay.
But I mean, it doesn't matter because, yeah, I think so. I mean, it just happens. And then because of the, functional completeness of NAND, you can build these arbitrary circuits. Okay, so in the case of quantum circuits, so a big thing in ordinary computers is program counters and looping.
Yes.
What's the analog in the quantum case? And by the way, even in neural nets, that's the story of recurrent neural nets and so on is the story of looping. I mean, neural nets in their simplest form are also these kind of just flow through Boolean network kinds of things that don't happen to be pure Boolean, but then the more sophisticated kinds of neural nets involve some kind of looping. What's the analog of looping in these quantum circuits?
Yeah, it's a really good question. I don't think this is well developed. People have investigated, analogs of loops in quantum circuits, but I don't think there's a generic formalism for it. That in that sense, quantum circuits are much more like conventional neural nets, right? They're a compute once thing.
Yeah, it just flows through. But that means, in terms of, I mean, really, they're just computing matrices, just like in. I just find it so confusing. What I mean, I'm still looking for what's the big thing you're getting out here, because yes, we can make a quantum Fourier transform with a certain, of a given size, with a fixed collection of gates, and I mean, I'm also a little confused by. I think these actual quantum computers work like field programmable gate arrays, in the sense that certain gates can be. I'm actually not sure how this works. How do you program it to have particular gates? Because you're creating a circuit, right?
Mm-hmm.
How does that work? Is it like an FPGA where you're basically switching on and off fixed pieces in a array of possible gates?
Yeah, another good question. And
we need a practitioner here of
right.
I think that's more or less how it works. But then
it must, yeah, I would have thought.
But can we imagine in a quantum circuit formalism of the kind we have here? Okay, so if we're imagining in our multi-way graphs, curiously, we do have the analog of loops because we have closed time-like curves.
Mm-hmm. Or we can do.
Right. And for example, our view, okay, so here's a question. Think about the harmonic oscillator. What is the implementation of a harmonic oscillator in terms of quantum circuits? So for example, your adiabatic, Hamiltonian formalism should be able to support a quantum harmonic oscillator easily enough.
Right.
Okay, so now what that means, I suspect, is a very boring thing in the quantum circuit. It means it's a periodic quantum circuit. Periodic in the sense that you've laid out a bunch of gates, cycle by cycle by cycle of the harmonic oscillator. You've got hard-coded gates that represent each successive cycle of the harmonic oscillator. Is that true?
Right. And I would have thought by the von Neumann mean-ergodic theorem that that should just converge to some unitary matrix, right? In the limit.
Interesting claim. So you're saying if there are stages, if you just go, it's like a Markov chain. You go ahead.
There's this theorem, the von Neumann mean-ergodic theorem, which just says if I continually compose unitary operators to each other, then they will converge to a unitary operator with respect to the strong operator topology.
I didn't know that. Okay, so let's try it. Write down a random unitary matrix, and you're saying that a high power of a random unitary matrix is, I mean, I suspect you need a determinant one random unitary matrix. We have random matrices, so I think you can do better than that. I think we actually have a random unitary matrix.
How do I call it?
Look up the documentation for random matrices, because I don't know.
Because I looked this up and I couldn't find a straightforward way of doing it. My approach is just generate a random matrix and then orthogonalize it.
Try, just look. We've got matrix ensembles.
Oh yeah, so we do.
But pull them into the screen.
Oh yeah, sorry.
Look at that unitary ensemble. Okay, Gaussian unitary matrix distribution. So random variate Gaussian unitary matrix distribution. Let's see that. Okay, so that should be a really. It just said unitary matrix there. Why? How come it isn't a unitary matrix?
Wait, matrices from the Gaussian unitary ensemble are Hermitian. right?
I don't know. I would have thought they were unitary based on the name of the ensemble, but I don't know. But why don't we look at the documentation for Gaussian unitary matrix distribution?
Okay.
It's disappointing that you're not using the in-product documentation, but this is fine.
Oh, sorry.
No, it's okay. The
so
okay, distribution of a Hermitian matrix. Oh, that's the Wigner circle distribution that you're getting out at the end there.
Right.
A unitary matrix distribution. So does it make unitary matrices? Could you look at background and context, see if there's anything there? Ah.
Yeah, it's an ensemble of Hermitian matrices.
Well, why is it called a unitary ensemble?
The appallingly named Gaussian unitary ensemble. I remember being confused by this when trying to read about.
Well, so what are the other types of? There's got to be a way to make. Okay, there is invariant and a conjugation by unitary matrices.
Circular unitary matrix distribution.
That sounds relevant.
Ah, yeah. Okay, this is what we want.
Okay, that's super confusing.
There we go.
Okay, terrific. All right, we got a friendly unitary matrix. All right, let's take a high power of that unitary matrix.
Right, so I believe
let's take. Well, yes, it's going to stay a unitary matrix. All right, so let's try how we characterize this matrix. We can look at the eigenvalues of this matrix, I suppose, as a characterization. Okay, so let's see those as a function. Make that parameter n. Okay, so now let's do a complex list plot of.
Can I just do that?
No, I think you can just do that, but that won't be the best. Okay, so I think what you should do is make a table of those eigenvalues going up to a high power. You could do it by mapping over the range if you want to, but I would do it starting at 1. I mean, and then okay. So now do a complex list plot of that. Let's see what that looks like. Okay, now I think you want to do a complex list plot of the transpose of that. Very unhelpful. Okay, then say complex list plot of first of transpose of eigenvalues. What the heck?
I may have got this theorem wrong. Okay, let me double
wait,
check.
Wait. Okay, but what this is saying is, given a unitary matrix that represents essentially one cycle of a, I'm very confused here. What I'm trying to figure out is, clearly the periodic circuit, a loop is like a periodic circuit, I think. A plain loop is just, you got a periodic circuit and you're feeding back into that periodic circuit. So I'm going to make the claim that it's not going to work in the end. There's going to be a squiggle here because it's not actually going to, you can't get an approximation to the harmonic oscillator for the same reason as the Hamiltonian versus the E to the IHT unitary matrix are transcendentally related to each other. You won't be able to get a finite block that represents the one cycle of the I claim. You won't be able to get a finite block that correctly represents one cycle of the harmonic oscillator. Therefore, what will end up happening is you'll, well, gosh, yeah, I don't even say. I mean, because what I was going to say is, the obvious quantum circuit is one that loops back those wires back to the beginning again.
Right.
But I think that's, and you can ask then, right, you could ask, what's the eigenstate? Can you represent that in this formula, in this framework at all? The thing where the wires loop back to the beginning?
No. No, not without some modification of how quantum circuit works.
But what that means is it's a consistency condition between, what the heck is it? It's a matrix. I mean, in your string diagram thing, it's you just connect the two ends of the string, so to speak, the one that's coming out and the one that's going in.
Right. Right.
How should one think about that? I mean, what is that? That's no longer a matrix multiply. That's some kind of eigenvalue condition, isn't it?
Yeah. Well, in the sense that it's a fixed point of some matrix multiplication, right?
Yes, that's right. Yes, with eigenvalue 1.
Right.
But that never happens, does it? Isn't there some basic linear algebra result that a matrix with eigenvalue, what is the math moment here? Given a matrix M, a vector, we have m dot v equals v, basically.
Mm-hmm.
For what matrices M, what's the condition on M and V such that M dot V can be equal to V? Isn't it trivial in some way?
I don't know. I know that being a Markov matrix is a sufficient condition for that, but I don't know the more general characterization.
What do you mean being what kind of a Markov matrix? I mean, in a standard Markov chain, there would be a lambda there that would be, you're saying the limit of a Markov chain?
It's not even the limit, right? It's just, the transition matrix for a Markov chain will have dominant eigenvalue 1.
Yes. Yes, fair enough. Okay, all right, fair enough. So maybe it is not so trivial to have, but then that would be the case, right? That's what you'd have if you connect the wires of the quantum circuit back to their start. You are requiring then you're asking, what are the eigenvectors? Yeah, it's a straightforward thing. The quantum circuit defines a matrix M. You are simply asking, normally in a quantum circuit, you get to give whatever input you want. Mm-hmm. But if you connect the wires back to the start, you do not get to give whatever input you want. In fact, the whole thing is completely determined by an eigenvalue condition.
Right.
So then the more interesting case would be something where some of the wires feed back and some do not. Because that's the case of essentially a thing with an input that has a loop in it. Mm-hmm. And I wonder what on earth happens in that case. I mean, that would be, that is something that the formalism, as you have it set up, should be able to answer. It is not specifically within this formalism because you're just defining the matrices that get multiplied together, but there's an overlay on that, which is actually solving the matrix eigenvalue problem.
Right.
Okay. So, all right, maybe we should try one last experiment or something. There's a question from SL8 here. Big thing to get out of quantum computing is ultimately we can see the discarded paths in the path integral. I don't think so. I think you end up, well, I mean, that's the question is, do you see the effect of those even after you've measured a particular result?
They're not really discarded, right? They're just destructively interfered.
Okay, we have a few more comments on the live stream on the chat here, which we can perhaps try and comment on. let's see. Calais is asking, can a chip be made that is essentially a matrix unit and connected to others? You can do parallel modeling, all obeying quantum mechanical rules. Yeah, I think that's what we were discussing about FPGAs, quantum FPGAs, and so on. I think we're not sure how that works, and I'm kind of embarrassed I should know that. TW is commenting here that doesn't the fact that we can only get the end results pose huge limits to quantum computers? I mean, we can't see any of the intermediate results in quantum computers. Yeah, that's kind of the not seeing intermediate results is supposed to be a feature rather than a bug when it comes to quantum cryptography.
Right.
But yeah, I mean, this is the big question of quantum computing: is how much effort does it take to measure a definite outcome? And let's see, there's a question from Jojo here. Is there a non-quantum analog of quantum entanglement, for example, something similar to the Borsak-Ulam theorem, which I do not know?
I don't know that either. Hang on, but I'm going to look it up.
I knew Stan Ulam, but that doesn't help me in knowing his theorem.
Every continuous function from an n-sphere into Euclidean n-space maps some pair of antipodal points to the same point. Okay, so it's a sort of pigeonhole. Presumably, it's a pigeonhole principle result.
Every continuous map from an n-sphere to what?
To n-space, so to Euclidean space.
Yes.
Will map a pair of points to the same point.
Wait a minute. So, like projections of the Earth, right? An example of this will map antipodal points to the same point.
Our projections of the Earth, they're
mapping a sphere onto a plane.
Are they continuous? I thought there are discontinuities, but maybe I'm wrong.
There are. Yes, there are. Yes, there are. Oh, I see. This sounds like more like a Banach-Tarski type. I mean, one might think it will be good to have a continuous projection, to draw your maps with a continuous projection, but I don't think that's possible.
Right. I'm okay. Interesting question, but I don't immediately see a connection with entanglement.
Well, I think the issue is maybe what you're looking at has information about that, but I would think, how do you make a continuous map from the sphere onto the plane with no discontinuities? Surely that's sort of a Banach-Tarski type story, isn't it? I can't see how you can do it without, in any sort of ordinary way, without grinding things up very small. Maybe I'm wrong.
I don't think this requires Banach-Tarski. I mean, sorry, I just quickly read through the proof. I've seen a popular version of this theorem in the proof that there must always exist antipodal points on the Earth that are at the same temperature. Right, and so the argument there is, okay, so suppose that, and actually that's true along any axis, because if the temperature is a continuous function across the surface, then if I take if I take a slice through through some plane of the Earth, and I just look at the temperature difference between antipodal points, that temperature difference will also be a continuous function, and when I rotate by pi radians, it will change sign. So there must be some intermediate. It's just an
intermediate value theorem. Yeah, that's nice. I didn't know that one. Yeah, that's nice. Let's see. There's a comment from Flying here about until implementing error correction, they can't have perfect qubits to create gates. Oh, that's its own separate can of worms.
That's true.
I mean, I just want to see us do something. I mean, I'm sorry, I keep on pushing on what's the most non-trivial thing we can do, right? Like we're going to set up to connect our quantum framework to actual quantum computers as anybody is claiming that there are. What are we going to do with it? Right? Let's say we've got our 5 minutes on a quantum computer. What are we going to do?
Right.
anybody on the live stream has suggestions, we'd like to hear them, because we can get our 5 minutes or much longer than that on quantum computers, but we'd like to know what to do with it.
Mm-hmm.
I mean, like for example, okay, so a question obviously we'd like to know is, well, here's a question. Can we see our maximum entanglement speed in a sufficient, how would our maximum entanglement speed show up in a quantum computer?
Right.
It means that in this kind of qubit space, well, what does it mean? Is there, with respect to, if we made a very big quantum circuit, would there be something about it in which we could see a maximum entanglement speed? I think there is. I think if we turn it into string diagrams and all these kinds of things, which is like turning it into kind of multi-way pieces, then there'll be some result that basically says you can't get to something about how you can't cross this string diagram faster than something or other.
Right, right.
So how would we do that? Let's imagine that we made a very big, we're simulating with our framework, representing with our framework, a very big quantum computer. Mm-hmm. What attribute should the very big quantum computer, actually, here's an interesting question. Okay, so ordinary computers have speed of light constraints.
Right.
Actually, this is a very interesting question, I think. Okay, so an ordinary computer laid out with, if we did a circuit diagram for an ordinary computer, the immediate thing that we'd start having to ask when we physicalized it is speed of light constraints. We've got, 100 million wires laid out, and they are, 3 centimeters from one wire to the other. There's a speed of light constraint on how long it will take to get from one wire to the other. In the quantum case, we've got, 100 million qubits laid out. The question is sort of how long does it take for one of those qubits to affect others?
Right, of course, yeah. I mean, that's what a maximum entanglement speed is.
Right, but why can't we?
What's the time difference if I have an arity 2 gate here and an arity 3 gate of the same type? What's the difference? What's the execution time difference?
Right, but so what would that look like in? Okay, so, but let's consider the much bigger case where we could actually. Okay, first question is, if we wanted to estimate the speed of light, assume Mr. Fitzo or whatever who was the guy with the moons of Jupiter? Who was that? The first person to measure the speed of light?
Yeah, I don't know. I know the story. I don't know the person.
Yeah, it was very, very early. I mean, it was in the 1600s, right? And then that guy with the toothed wheel, Fitzo, I think, actually measured it terrestrially. My question is, if all you're given is a microprocessor, can you measure this? Oh, yeah, that's the right one. Yeah, Roma. Okay. If all you're given is a microprocessor, can you deduce the speed of light? Mm-hmm. Or if all you're given is a memory chip, is there any way to know the speed of light? Let's say you have a very big memory chip and you're looking at its characteristics. How can you, in other words, is there a way of, you sample this piece of memory, you sample that piece of memory, there's a minimum time. Well, it's all going to be hidden by the cycle times in the circuit. I think that's it. I hadn't really internalized that. I mean, the design constraint on a classical circuit is there's a speed of light design constraint. On a quantum circuit, as normally done in the quantum information framework, there is no speed of light constraint. You can have as many qubits as you want laid out, but there should be a maximum entanglement speed constraint. And my question is how to understand what that, I mean, it should be the case that in these matrices, that sort of poking one qubit can affect distant qubits only at a certain rate. Or alternatively, the qubit light cone can only expand to affect other qubits at a certain rate. Am I right? I mean, but how would we think about this in these circuits? I mean, what's the minimum? Okay, here's a question: what's the minimum extensible quantum circuit that isn't totally trivial? In other words, if I just want to make a quantum circuit with 100 million inputs, what is a reasonable circuit to make?
Yeah. Well, I mean, I'm sorry. I completely don't understand what's happening anymore. Yeah. So yes, what you've just described is the maximum entanglement speed, as we've.
I know, but I hadn't internalized that this could actually be a constraint. Like, you're an engineer, you're trying to design a big quantum circuit. This is a constraint, just like the speed of light is a constraint in designing ordinary classical microprocessors. And so I'm just trying to understand, given that constraint, how would it show up in circuit design, right? In other words, for example,
like I said, but I don't. So what I said earlier about, like measuring time differences between arity 2 and arity 3 cases of the same gate, like why is that not?
Because I think that's like saying,
in fact, you don't need, one doesn't even need arity. I mean, you could do all of this with an arity 2 gate and just with higher entanglement entropies.
How do you make those?
Oh, that's just a state preparation thing, right? So if we say
for the superposition that has more, which is more superposed, so to speak.
Right. So if I create a 2-qubit random state like that, and I can say, well, so there are various kind of distance measures that I can do. So like I can ask what's the if I took two such states. I could ask, what's the difference between these? What's the distance between these two states in Hilbert space? It gives me the concurrence distance. I could also ask for like the trace distance or the fidelity distance or something. I think I can ask for the relative entropy distance, which may or may not be defined. Oh yeah, okay, it is defined. But more interestingly, I can also ask within a state itself. I can ask, well, first of all, are a particular pair of subsystems entangled?
Yep.
Of course, it's an arbitrary pure state, but I can also quantify that. I can say, what's the entanglement monotone? So this is going to use, by default, this will use quantum concurrence as the entanglement monotone.
What's the definition of that?
So that's just given in terms of traces of the product of the density matrix with itself.
Okay.
But then there are also other kinds of entanglement monotones I could use. So like I could, there's this so-called Perez-Horodecki separation criterion, which is based on negativity and logarithmic negativity. So I can ask, like, what's the like?
Right, but anyway, we've got some measure of how entangled the state is, how much it differs from being just a basis state, basically.
Right, and so then if I asked for like, if I take a maximally entangled state like GHZ, and I say, what's the entanglement between? So all of these are like between 0 and 1. But if I did this for like states 1 and 2.
Yeah, you want 2 for that one.
And I want, so this is tripartite entangled. So this is a GHZ. This is telling me that GHZ is a maximally entangled state, right? So subsystem 1 and subsystems 2, 3 are maximally entangled. So what you would care about is now if I use these, if this is my state preparation step and I now apply a circuit to this, an arity 2 or an arity 3 circuit, what one would expect is that the same gate should have a greater execution time for the GHZ state than it would for this state, because the entanglement is higher.
Well, let me understand that. So really, that would be an actual way to measure maximum entanglement speed. Why would it have, so when you physicalize this in some ion trap or some such other thing, I don't even know how you do, clocking for these things. Right. Because what you're claiming that I think we need to understand more about how these are physicalized, because you're claiming that, okay, normally in one clock cycle of a microprocessor, you expect certain, electrons to move around and they've finished doing their thing by the, and all the sort of wiggles from the, RLC circuits have died down by the time you say one clock cycle is over, right? And so presumably there is an analog of that in the quantum circuit case. And you're making the claim that even if I just solve the Schrodinger equation, I mean, you should see this just solving the Schrodinger equation, shouldn't you? That all the little wiggles of the wave function as a function of continuous time will take longer to die down if the initial data is a more entangled state. Is that correct?
Potentially. I'm making a much more basic point, which is just that when converted into a string diagram or a multi-way picture, these entanglement monotones are measuring distances between the subsystems in branch yield space, or through slice of the string diagram or something. And so if it is the case that there is that evolution in branch yield space is hyperbolic rather than elliptic, then there's a maximum signal velocity, which means that in order for you to apply an arity2 gate to it, you're limited by that maximum signal velocity.
Yeah, I understand. I'm just asking whether you should be able to see that in quotes classical quantum mechanics. In other words, if you have an actual ion trap thing, it presumably satisfies the Schrodinger equation.
Right. Yeah, but the problem there is that the Schrodinger equation, okay, it depends what the definition of your time parameter is, right? That's the key problem. So the question is,
because what we're doing is something. I mean, quantum circuits don't really have a notion of time in them; they just do their thing.
And also, I mean, obviously, this gets a bit confused when you start thinking about the Dirac equation and relativistic QM and things. But the Schrodinger, the notion of time in the Schrodinger equation does not have this notion of sort of quantum relativity built into it, right? It's
what quantum relativity? What do you mean?
In the sense that the subsystems, okay, this notion that the subsystems interact, as a hyperbolic system with a maximum signal velocity rather than as an elliptic system with an infinite signal velocity, is some kind of relativity principle in quantum mechanics.
Indeed, right. It's a relativity in branch yield space as opposed to in physical space.
Right, exactly. But the definition of the time parameter in the Schrodinger equation presumably does not accommodate that.
Well, the Schrodinger equation is a diffusion equation-like equation, which no doubt approximates that in the same way that the diffusion equation approximates molecular dynamics. In other words, the diffusion equation says that in principle there is a tiny effect an arbitrarily long distance away. The effective speed of sound in the diffusion equation is infinite. The expected speed of molecules bouncing around is infinite. There just are an infinitesimally small number of molecules that, according to the diffusion equation, reach arbitrarily far out in arbitrarily short time. But so I'm sure the Schrodinger equation is the same way.
Right. So the point is simply that just like, okay, in the classical computation case with speed of light restrictions, I could define a gauge choice, right? I could define a universal time function for space-time that made it such that my circuit appeared not to have any speed of light constraints with respect to that time function. Right? There is a gauge choice which makes that happen.
I don't think you can make that consistent for arbitrarily long, but you can do that for one. I don't see how you can expect to do that, because you can do it for one step, but how can you do that? How can you continue to do that?
No, mathematically I can, because I can make any arbitrary gauge choice that can be obtained by by diffeomorphism. But the problem is, as you say, physically that is a really difficult thing to do. I need some weird state.
Right, but your gauge choice is going to depend on the input to the computer, which is a complete cheat.
No, it's a completely pathological thing, which requires some variable gravitational field or something. But in principle, there is a gauge choice that makes it such that.
Right. Okay. So what you're saying is, given you can make a gravitational redshift, so to speak, so given that you know what actual bits are flowing through the computer, you can distort space-time to the point where you can come up with any conclusion about the speed of light. Given that you can predict in advance in a Maxwell's demon kind of way what the actual flow of electrons through the computer is going to be.
Right. So importantly, mathematically, I could write down an equation whose gauge choice, had that as its time parameter, in which, this finiteness of the speed of light would not, it wouldn't appear to be a feature. And all I'm saying is, presumably, the Schrodinger equation has implicitly made such a gauge choice, because it's not accounting for this effect.
Probably. I mean, or put another way, I mean, people make coupled Schrodinger equations for different quantum amplitudes with wild abandon. They don't think about, I mean, again, the quantum circuit formalism does not have a notion of time. You talk about propagation delays. I mean, you could fake in time by saying, as you go through this quantum circuit, every step in the quantum circuit represents 1 unit of time.
Right.
How do people normally do this in quantum? I mean, in quantum complexity theory, what do they normally do?
Oh, they talk about gate complexity rather than time complexity.
That's a wimp out.
It's the same in Boolean functions, right? People talk
I know, yes, I know. Well, interesting. But okay, wait a minute. You've got me very excited about the possibility that there could actually be an experiment that would measure maximum entanglement speed. Because we've talked about this for ages, about whether you could actually build a quantum computer that could measure maximum entanglement speed.
The problem is, I don't know how much timing. So the openly available quantum computers, such as they are, I don't know what kind of timing information is extractable from them.
Well, that's a separate problem. I mean, if we can define a system, I suspect we can get somebody to build it. I mean, I think that the only question would be, given if in my 5 minutes with a quantum computer I could measure maximum entanglement speed, that would be totally thrilling. But I would be absolutely amazed if that's possible.
Right. I mean, if there is timing information given, then in principle we could do that, right? Because as I say, all we'd have to do is define a simple 2-qubit circuit, and then do two different state preparations, one with low entanglement, one with high entanglement, and see.
Yes, but this is profoundly not going to work because it's the same reason. A circuit designer, given any circuit, any actual circuit has RLC stuff in it, so it's going to wiggle around. The actual voltage and current and so on are going to wiggle around. And you say my clock cycle is finished when everything is more or less quiescent. There's an exponential decay, but the exponential is never going to go to actually identically zero. But it's good enough at this point, and I can go and do the next clock pulse or whatever. So similarly, I guarantee that the way these quantum computers are being set up, they have a definite clock pulse timing period, and that's just computed, and that to ask the question, which one could do, but one would have to go below the level of the circuit idealization, so to speak, the quantum circuit, quantum gate idealization. This is below the gate level. It's at the discrete component level.
Right. So you don't think we're going to be able to do this with the open Qiskit API anytime soon?
No, I'm sure that it specifically idealizes this away. I think what one might be able to do is take the quantum computer hardware and make more detailed measurements that actually are measuring. See, but then there's another can of worms here, because anything one does there, one is doing through a quotes quantum measurement. And what we're looking for, so we have to do repeated measurements. Well, look, this is at least a definite objective, right? So how do we make perhaps the right thing is some kind of quantum array. Maybe it's some array of Josephson junctions or something. It's some kind of thing where there's a bunch of quantum devices in some large array, and then you're making the claim. Oh boy, you see, you're making the claim basically that the time it takes for the system to kind of come to equilibrium is longer when it is a more entangled initial state.
Well, yeah. I'm actually saying something a bit simpler than that, which is just that the analog of physical distance between these wires is presumably the entanglement monotone between the associated qubits. Or at least, in the branchial space picture, that's what it is.
Yeah, I think that, right. I think but in the branchial space that we're used to is discretized on the multi-way system, whereas these things you're dealing with here are real, complex numbers in the initial states. So I think that's confusing as well, because I think that then if you want to decompose that in terms of something like the graphs that we're used to, you're going to be doing something like the ZX calculus thing where you have a particular phase angle and you're decomposing it using that particular phase angle.
Right. Yes, exactly.
And so I claim that your computations here are very continuous math and maybe confusing with respect to what we're, the intuition that we have from multi-way systems. But well, okay, this is very interesting. I mean, to me, this is a definite objective of figure out, how do we formulate the question? I mean, I just wonder, with maximum entanglement speeds, as we kind of guesstimate they might be, the question is there any way of estimating, like given timing information? Let's imagine that we have timing information to terahertz type levels, so 10 to the minus 12 seconds in well, we'd have to go work this out. I mean, the question is whether our estimates of maximum entanglement speed, it's hard to know what that, I guess, yeah, we also haven't talked about energy, which also doesn't show up in these quantum circuit idealizations.
Right.
Right. I mean, it does in the adiabatic case, but it doesn't in the ordinary, in the ordinary quantum circuit case, you're imagining that you're sort of driving data from one side to the other, and there's no discussion about energy.
Right. Yeah, exactly.
Yeah, well, okay. There's more to untangle here, but this is interesting, and we should probably wrap up now. Is there one last question? DV comments, there was an experiment done in 2013 bounding the speed of spooky action at distance, which experimentally determined a lower bound on the entanglement speed.
But presumably that was entanglement speed in physical space.
Yeah, in physical space, it's a different thing.
Not quite the same.
Yeah, that's a very different thing. I mean, what do we say about, I mean, there is no direct relationship between entanglement speed in branchial space, and physical space.
There is in a sense, right? Because the more physically extended something is, the more branchially extended it is.
With respect to it, otherwise curls itself up into a black hole or something.
Right. So it should be the case that the entanglement speed in branchial space gives you some trivial bound on entanglement speed in physical space, but it may not. But given how much greater general branchial extent is than physical extent, I suspect that bound is not very strong.
Well, I think there's going to be a gravitational constant somewhere in the relationship between those two pieces.
Right.
In other words, it's going to be essentially it's going to be related. I'm not quite sure. I can't do the dimensional analysis immediately, but it's going to be related to black hole-like Schwarzschild radius-like things, which, for all practical purposes, will make the speed of the entanglement speed in physical space look infinite.
Yeah, no, I agree. It'll be huge. Like, yeah, the bound I don't think will be useful.
But we should work out what it is, because if we can actually work out what, because people do imagine in quantum mechanics that entanglement happens at infinite speed.
Right.
In physical space, across physical space at infinite speed.
And then all we'd need is a qubit that happens to be entangled with something that was on the opposite side of the universe during the inflationary epoch, and then we're good.
Well, but what's your point? I mean, that then we can hop across the universe with.
Oh, yeah, that's a good point. Yeah, we need an observer on the other end who's able to communicate with us.
Right, and then you need completions, and you need just all kinds of. I suspect there's actually. I think that's an interesting question. I think the question of whether in our models there is a maximum physical space entanglement speed is a reasonable and interesting question. So thank you for that that piece of input. All right, I think it's time to wrap up. By the way, for people who are interested in this, oh, Anders is making a comment here about quantum communication seems more interesting to me. And this shows the result of broadband low frequency radio using quantum detectors. Don't know about that. Anyway, for those interested, tomorrow we have this event about post tag systems with featuring various people, including people who, one person at least, who actually knew Emil Post. And the subject is, it's been 100 years since Emil Post invented his tag system and discovered that it was a difficult thing to deal with. What have we learnt? And can we finally solve the problem that he posed 100 years ago? So that's coming up tomorrow afternoon, and people are invited to join us for that. All right. Well, thanks a lot to everybody. Thank you, Jonathan. And let's wrap up here for now.